Okay, so hello everybody again. This is Rafiqul Ghani. We will start the webinar 1 now. And today's webinar 1 is the first in the series of PSE for Speed webinar series 2022. And I have the pleasure of introducing Professor Venkatasubramanian, who will talk about AI in chemical engineering, past, present, and future. Let me give a little bit of introduction to Professor Venkatasubramanian. He received his BS in chemical engineering from the University of Madras, his master's in physics from Vanderbilt University in USA, and his PhD in chemical engineering from Cornell University in USA. He's a fellow of the American Institute of Chemical Engineers, which also awarded him the Computing in Chemical Engineering Award in 2009. That is the CAST, Computing and Chemical Engineering Award. He joined the faculty of Columbia University School of Engineering in 2012. Prior to that, he taught chemical engineering at Purdue University, where he won the Norris Shreve Prize 3 times for his outstanding teaching. In 2015, he was the Roger Sargent Lecturer at Imperial College of Science, Technology, and Medicine in London. His 3 papers on hazards and risk analysis, published in Computers and Chemical Engineering Journal in 2003, are still among the top 10 most cited papers in the journal. His perspective paper from 2019, published in AICHE Journal on the promise of artificial intelligence in chemical engineering, is it here finally, is the top cited paper in the journal now. He also wrote a very interesting book called How Much Inequality is Fair? Mathematical Principles of a Moral, Optimal, and Stable Capitalistic Society. He published the book in 2017, and I recommend this book very much if you are interested to read. Professor Venkatasubramanian's research interests include risk management, material science, emergence, income inequality, artificial intelligence, statistical mechanics, game theory, and systems engineering. For today's lecture, Professor Venkatasubramanian cannot give the lecture online at this moment because he had an emergency eye surgery, so he kindly recorded the video a few days ago. And we will play this video, but he will be available for question answer after the presentation. So please do stay on and join the question answer session and have a good discussion with Professor Venkatasubramanian. Now the host will start the video. Thank you very much and enjoy the presentation.
Good afternoon, everyone. I'm delighted to be here, even though we're present only virtually. I'm very grateful to Professor Rafiq Ghani for kindly inviting me to present my work to this audience. So we're going to talk about artificial intelligence in chemical engineering. And well, there is a lot of excitement about AI these days, and particularly about machine learning, and one might, with the impression that this is a fairly new opportunity. Well, actually, AI in chemical engineering is not all that new. It has a 35-year-old history, dating all the way back to early 80s. And by my estimate, there are more than 3,000 papers on AI in chemical engineering that's been published already in various topics. So what I plan to do in today's presentation is to give you a highlight of what happened in the last some 30 some years, and particularly identifying the challenges and opportunities that we have going forward. But I will emphasize conceptual challenges much more than implementational and organizational difficulties, even though those things are important. But the conceptual challenges are where we, as academics, can have an impact. It's a broad overview, not a very detailed technical presentation. For some of the details, you can refer to a perspective paper I published some 3 years back. So I divide the different eras of AI in chemical engineering into phase 1, phase 2, and phase 3, and so on. So the earliest era, the phase 1 part of AI in chemie, is the era of expert systems, or what I call a symbolic AI. This started, as I mentioned, in the early 80s and lasted for some 15, 20 years. And the idea was to develop computer programs which were as good as the human experts in that particular domain. For example, here, it would be a doctor, a physician, whose expertise in diagnosis and diseases is what we want to capture in a computer program in this kind of a format. So some of the key ideas from that era was dividing knowledge into domain-specific knowledge and separated from the inference engine or search. And so that was a key conceptual breakthrough. And this was aided by the flexible execution of the order of the program within the inference engine that made such a separation possible. And then the representation of knowledge in the form of if-then rules for procedural knowledge and the semantic networks for taxonomies was another key idea. So all these things were implemented in the first expert system that was developed in the 70s called MySyn. It was for diagnosing infectious diseases. It was a joint project between computer scientists at Stanford with the Stanford Medical School physicians, funded by DARPA, the Defense Department of the US. At the end of the effort, the system had about 600 rules that are specific to infectious diseases diagnosis, and it did very well. It was better than the 6 physicians who were consulted in developing the system, and it did diagnose better than the physicians. So this got a whole bunch of us excited in chemical engineering around that era. And Art Westerberg at Carnegie Mellon did the first work on developing an expert system in chemie, along with his PhD student, René Benyares Alcantara, my good friend, who is now a professor at Oxford. So René developed this confined system for predicting thermodynamic properties of complex mixtures for his master's thesis. And then he later continued for his PhD catalyst design system. Around the same time, I was setting up my AI lab at Columbia to focus on fault diagnosis, an area which I continue to work in. And around the same time, Professor Stephanopoulos at MIT was setting up his AI group to look at design problems. And Jim Davis also design-oriented effort at Ohio State. The first course on AI in chemie was taught at Columbia in 1986. I taught it there for 3 years, and then I continued teaching it for the next 20 years or so at Purdue. And then now I'm back at Columbia teaching it again. The course content has, of course, evolved over the years. And I have a paper coming out about that in the next month or so. The first conference on AI in chemistry was held at Columbia as well in '87. So one of the highlights I want to point out is this ASM consortium. It stands for Abnormal Situation Management Consortium, that was organized by Honeywell with all the leading oil companies as participants. Exxon and Mobil were two different companies at the time. And the goal was to develop next generation control system, what we call as intelligent control, where the regulatory control layer has been automated for 50, 60 years. Now the challenge is the automation of the next layer, next level up, which is the supervisory control layer, where operators, we still depend on operators to do alarm management, alarm interpretation, fault diagnosis, etc. And so can we get AI to do those kinds of tasks as well? And that was the goal of this consortium. And it was funded by the US government as well as the oil companies. 3 university groups were invited to be part of this. Jim Davis at Ohio State, and then I was at Purdue at the time, and then Kim Vicente from University of Toronto. This project or this program is actually the forerunner to the current Smart Manufacturing Initiative that got funded in 2016. If you look at the goals of the Smart Manufacturing Initiative, they're all pretty much the same as what we wanted to do in the ASM programs 20 years before. So as part of this, my students and I developed a diagnostic toolkit. We call it DKIT, and which is an AI-based system that had both mathematical models, such as observers, as well as cause and effect relationship models, such as in digraphs, trend analysis systems in QTA, expert rules, and neural networks and PCA-based systems as well. So these are the different expert physicians looking at the patient being a chemical plant. And we have real-time process data coming in. And then the goal is for these physicians to assess the state of the plant, whether it's normal or abnormal, and if it is abnormal, what's wrong with it, and make the appropriate recommendations to the operator. And as part of this, it would detect deviations from normal behavior and alert the operator and provide the diagnosis. And it was implemented in this expert system environment called G2 and tested at the Exxon Chemicals company in Baton Rouge, Louisiana. We were given real-time data, roughly about 500 data points every minute of set points, valve positions, pressures, control, temperature, flow rate, concentration, that sort of thing, and then see whether it could diagnose failures. Well, DKIT successfully diagnosed failures even before the alarms go off, because the alarms typically trigger in only after a threshold is reached. But DKIT was able to capture even the earliest deviations and sort of like an incipient fault, and make the correct diagnosis and alert the operator roughly anywhere from half an hour to 2 hours before the alarms were triggered. So this really impressed Honeywell. And so Honeywell licensed DKIT from us at Purdue, and this is the first software licensed by any control vendor for intelligent control applications. And so the idea was, we had a research prototype, and then they were going to take that and then transform it into a commercial grade software. So how come we haven't heard about DKIT in the last 20 years or so? Well, as it turned out, the organizational and the implementational challenges were just too hard, something I'll talk about in the next few slides. And so it was hard to scale it up to industrial settings. And so looking back, I realized that we were about 20 to 30 years too early to attack this problem for practical impact, even though we showed how to formulate this problem, how to solve it, and we showed, demonstrated its capability on actual real life industrial data. But to go from there to routinely used commercial system, the implementation organizational difficulties were just um, too daunting in those times. And so as part of this, I just want to give you an idea about what kind of techniques were used. We developed multi-scale causal models because diagnostic reasoning involves cause and reasoning about cause and effect relationships. From causes, you want to go to consequences. You want to reason backwards from consequences to causes. That's diagnosis. And so we developed this multi-scale model where you could take a process flow sheet, zoom in on any particular subsection, and then get to the actual unit, and then model the cause and effect relationships using diagraphs. These are graph theoretical models. And then for batch processes, you need to, in addition to that, you need to add the recipe of the process as well. So here is, and for that, we use another graph theoretical technique called Petri nets. These are techniques which are better known in electrical engineering, not that much known in chemical engineering. In fact, our paper was one of the earliest in demonstrating the use of such formulations. And so here is a recipe Petri net, which talks about a three-step reaction, process, reaction, filtration, drying. And each one of those steps, tasks themselves, have multiple subtasks, and which also can be modeled by Petri net. So you have this hierarchical multi-scale models, and then each one of those elements have an associated digraph model as described in the previous slide. So this was the story of AI-based fault diagnosis and DKIT. So here again, like as I said, in diagnosis, you go from symptoms to causes. And now the forward problem is the prognosis problem, which is where process hazards analysis comes in. So this is where you want to go from, you want to create abnormal causes and see what kind of adverse consequences would occur. So we built such a system also called PHA Suite. And this was the first AI-based system to do process safety analysis kind of reasoning. And it had a library of some 50, 60 different causal models of the various units that you typically find in chemical and pharmaceutical plants, reactors, pumps, valves, distillation columns, and whatnot. So when you connect these things on the screen and create a flow sheet, it can automatically analyze all things that can potentially go wrong in each one of those units and their connections, and then organize them in a particular way. It was tested on 20-some industrial case studies, both continuous and batch case studies, and it typically captured 95 to 100% of the human team's analysis results, but in half the time. And it's at about 500,000 lines of code implemented in largely C, C++, and Java. And it took the efforts of 4 or 5 PhD students over 5 to 7 year period. And so let me then talk about operator procedure synthesis related to the same kind of batch process operations. So here again, the problem is to generate detailed sequence of instructions and operator needs to manage a process safely and optimally. And it's a very important task in pharmaceutical companies, done every day, even today. And it consumes a lot of time and effort and money to write these things and then validate them and to make sure they are safe and whatnot. And so we felt, well, AI could possibly help. And so we developed a system called ITOPS. It stands for Intelligent Tool for Operating Procedure Synthesis. It's an AI-based system. And it was developed around 95 to 98, and it was delivered to the Searle pharmaceutical company in Chicago, which got acquired later on by Pfizer. And I won't get into the details of it, but I just want to show you how the overall framework looks like, the modeling framework. We have declarative knowledge, such as knowledge about process material, process chemistry, process equipment. which is modeled as shown using object-oriented programming ideas. And then the procedures you were modeled using graph chart procedures, similar to what I mentioned earlier in Deacon. And then the problem solving requires knowledge representation along these lines, and then planning, and where you have to identify the path, search, and equipment assignment first. Then comes preliminary sequencing, then comes the final sequencing, and then the final operating procedure synthesis. The details are discussed in our papers, and you can look them up. And so this was tested on 50 different batch processes at Searle, and it was shown to be doing, savings about 50% of time and effort. And particularly it created fewer errors, and it was used by some 25 different process engineers in 1988 in their daily operation at Searle. I'm going to switch gears now and talk about design, particularly inverse design of materials, where we showed that to do this in an automatic fashion, you really have to solve two related problems. One is the forward problem. Given the structure, how do I predict the properties, macroscopic properties of the materials? And the design problem is the inverse problem. I know what properties I want here, but I don't know what product structure or formulation will get me there. So we showed how to do this using directed evolution or genetic algorithms. And for the forward problem, we used a hybrid AI model, which is part first principles based and part neural networks. And then the inverse problem using directed evolution, where genetic algorithm with a priori knowledge, we could create sensible structures and sensible chemistries by putting that knowledge in there. And so we showed how these things can be used to develop, design actual industrial scale problems, such as design of fuel additives for Lubrizol company in the 90s, and then rubber compounds formulation for Caterpillar also around the same time frame. Around the same time, Professor Frances Arnold at Caltech was also pursuing directed evolution, but in vitro. We were doing it in silico. She was doing it in vitro to design enzymes. We were designing polymers and fuel additives and rubber compounds, and she was designing enzymes in vitro. It turns out this idea of directed evolution is important, not because I say so, but the Nobel Committee said so. Professor Arnold was awarded the Nobel Prize for this work in 2018. So as part of this inverse design problem, we later on developed a system called Reaction Modeling Suite for ExxonMobil, and where for catalyst design, where it was again a combination of symbolic AI in the form of chemistry rules and chemistry compilers, and then neural network components embedded in them. So you go from the initial hypothesis, and the compiler automatically translates that into detailed microkinetic reaction network on the surface of the catalyst. This was a heterogeneous catalysis problem. Then it automatically generated all the algebraic and differential equations, solve them, and make predictions. And typically, you won't get everything right in the first go, and this is an iterative procedure. And based on what worked and what did not work, you go back and revise our hypothesis, etc. So the novel features where this was the first time a domain-specific language for reaction chemistry was demonstrated. A domain-specific compiler was built, a chemistry ontology was developed, and the technique, which now people call as active learning, was proposed in this context at that time. So that's all happened in the first phase of AI in chemical engineering. And now moving on to the second phase, and this is where neural networks entered the picture. Now, as it turned out, the expert systems just took too much time, effort, and specialized expertise to develop. And so as a result, they did not scale well for industrial applications. And around the same time, the backprop algorithm was rediscovered by Hinton and company at Carnegie Mellon. And there they showed how a neural network can be trained to learn the correlation between input data fed to the input neurons and then the output data shown to the output neurons with hidden layer. And this was a bottom-up strategy where the system automatically learned these patterns. And as a result, that made it easier to develop such systems. So this again set off another revolution in AI applications in a variety of fields, including chemical engineering. And particularly because these neural networks were shown to be universal approximators, that means they could do nonlinear function approximation well and nonlinear classification problems well. So this generated a lot of papers in process control and fault diagnosis in the phase 2 era. So in the first 30 years of AI methods in chemical engineering, pretty much its possibilities were demonstrated in all aspects of chemical engineering, in monitoring, diagnosis, and that control that I talked about, design, process synthesis, safety analysis, optimization. I didn't talk much about planning, scheduling, but that was shown also. So prototypes were demonstrated in all these areas, and in some in some cases, even industrial applications were fielded, like the work we did for Lubrizol and Caterpillar and ExxonMobil. So why was AI not impactful in chemie during those decades? If all this progress had been made, how come we didn't hear about it? We are hearing about AI only in the last 5 years. Well, largely because, as I said, they remained as research demonstrations, didn't scale well for industrial application because the implementation and organizational difficulties were huge. And that was because of lack of computational power and computational storage. We were working with very, compared to now, really relatively weak machines, and memory was expensive. There was no communication infrastructure. In fact, when my students and I were doing the early work on AI, internet had not been invented. And that internet appeared only in 1995. But a lot of AI work had been done between 1985 and 1995 already. Lack of convenient software environment. My students were programming in Lisp, this archaic AI language. That's nothing like working with Python libraries where a lot of the things that you want to do are already available. In this case, you really had to build them from scratch in Lisp. No specialized hardware such as GPUs, lack of data. It was not a big data era at the time. And so as a result, the costs were prohibitive. And essentially, it just took too much effort, time, and money to field industrial applications. That is, AI was just too hard in those years. Doing AI was just too hard. And as a result, like I said, we were too early by about 20 to 30 years. Now, what is different now? Why am I excited about AI now? Well, in 1985, when I got started doing AI at Columbia, the biggest, baddest computer we all wanted to get our hands on was this beast called Cray 2. You can see from the figure here how big this was. You know, your people standing here, and this is Cray 2 and its peripherals, and it was a huge machine, and it took up a lot of space. It required several thousand square foot of space of air-conditioned space, that too, because it consumed 150,000 watts of power. So that put out a lot of heat, and you needed a massive cooling system. I used to joke that Cray was really a space heater, which did computing on the side. And it also cost a pretty penny, $32 million in today's dollars, half of that in 1985. So it was very powerful, but very expensive. And so what would Cray look like today? Now, if I were presenting this talk in person, at this point, I would raise my left hand and show you my Apple Watch. The Apple Watch, in fact, I'm wearing the most recent one. And if you look at the first generation Apple Watch, which is 2015, it is more powerful than Cray 2. 3 gigaflops of speed. Gigaflops of computational power, 1 gigahertz, and it consumes just 1 watt of power and costs about $300. So if someone had told me in 1985, Venkat, you want Cray, right? Let me promise you that you will not only you not only have an access to Cray, but you will actually own it, and that it will be on your wrist. If somebody had made this prediction in 1985, that person would have been admitted into the lunatic asylum the same day. Nobody saw this coming. This is a performance per unit cost gain of about 150,000 fold. Getting a Cray on your wrist for $300 is a game changer. And this is why AI is here today. Okay. So how did this happen? Well, it all happened because of one thing, really, really one thing, which is Moore's law. As you may recall, Gordon Moore, one of the founders of Intel, made this prediction in the 1960s that the transistors would double in their power every 18 months for the same cost. And he said this may go on for 10 years, maybe 20 years. But even Moore did not see this happening for the next 50 years. We really got a bit lucky there. And also the ingenuity of the chip designers, that they kept the Moore's law going for 50 years. That kind of compounding of doubling every 18 months is why AI is here. And it is why Apple Watch is here. That is why internet is here. And you can see from this log plot of this linear progression going from these earliest computers to the more powerful ones. And so all because of Moore's law, all these things improved. We got very powerful computers for very cheaply. Memory became cheap and abundant. Internet became possible because of Moore's law. Convenient software infrastructure environments like Python, Java, Julia, OWL, and all that became possible because of Moore's law. GPU arrived because of Moore's law. And because of all that, we are putting sensors everywhere and getting data everywhere. And so we entered big data era. So we started getting lots of data because of Moore's law. And so essentially, it has become a lot easier and cheaper to field AI-based solutions now than compared to 30 years ago. And it all happened because of one thing, which is Moore's law. So with this, we entered the third phase of AI in chemical engineering, which is the data science era, the current era of machine learning 2. And there are three important ideas here: the deep neural networks, reinforcement learning, and statistical machine learning. And all these help us do hierarchical feature extraction, as shown in this figure on the right-hand side. These are all important ideas, but not really all that new, as you'll see in the next slide. What is new are these things. We have more data, powerful GPUs, and easy-to-use software. So it is in this order of importance. These are the three things which are making AI now a lot more democratic, a lot more accessible to lots of people. And that's why we have Watson, Siri, and a second, let me take care of this. Sorry about that. And okay. Right. So because of that, we have Watson, Siri, Alexa, and AlphaGo, and whatnot. So going forward, the challenges and opportunities. So I just want to, kind of warn you about this hype cycle that I see now. There's a lot of promises being made, which are not feasible. I've lived through two such hype cycles already. I very much recall all the wild promises made about expert systems in the 80s and the neural nets in the 90s, and I see similar things with the data science and machine learning now. There are useful things we can do with the current tools of machine learning, but people are underestimating the difficulties of certain classes of problems, which I will talk about in the next few slides. So one is that a lot of the new techniques that people are proposing are really old ideas from 20 to 30 years back. For example, the self-driving car, is not all that new. It was demonstrated, believe it or not 5 years ago, not 10 years ago, but 25 years ago. In July 1995, this minivan drove itself from Pittsburgh to San Diego. Most of the distance, except for the city traffic of about 50 miles, it pretty much drove itself. So self-driving car was demonstrated in this Look Ma No Hands project at CMU 25 years ago. So what is new is that that was a multi-million-dollar project, and it required a minivan-sized vehicle to put in all the hardware. Now all those things have compressed, and so you can have those modules for a few $1,000s instead of a few $1,000,000. And then you don't need a minivan, you can put it in a Volkswagen Bug. So what is new is that, the cost has come down, the footprint has come down, and of course the algorithms have gotten somewhat better, but the idea is not all that new. The deep neural network idea was first proposed in 1990. And the autoencoder neural network was published in 91. Not only that, it was actually done by a chemical engineer, my good friend Mark Kramer from MIT, published in a chemical engineering journal. That paper appeared in AICHE journal. Okay, so you can see people were way ahead of their times in thinking of these ideas. Inverse design of materials, like I said, was demonstrated in the early 90s. Causal models were built in the early 90s. Explainable AI was demonstrated then. Hybrid models of combining first principles with data-driven techniques is not new. So to the young folks, I would certainly say it's worth reading the old papers because there are some really cool ideas in there. The other one is that we don't really need deep neural nets and reinforcement learning for many problems in chemical engineering. Often simpler and more transparent AI techniques are often adequate. And the challenge here is that many problems in chemistry and material science are not big data. We certainly have more data now than we did 10, 20 years ago. But we are not generating terabytes of data like they do in game playing or vision or speech. So we have limited data, but we have prior knowledge. Our processes and systems are all governed by first principles knowledge. So how do you exploit and leverage that along with data science is one of the challenges going forward. And the third complaint I have about the machine learning systems, such as the self-driving cars, is that they may do a great job of, for example, driving through Manhattan. Traffic, maybe do better than many New York drivers, including myself. But do they understand, do these systems understand the underlying concepts such as momentum and acceleration and force and Newton's F equals ma and so on? They don't. In my mind, it is the behavior is a bit like the cheetah chasing a gazelle in what you see in National Geographic videos. Both animals display a great mastery of the dynamics of the chase, but both are clueless about the underlying physics, which is classical mechanics, and the underlying math, which is calculus. So in my mind, current AI systems perhaps have achieved this animal-like mastery of their domain without gaining a deeper understanding. And as a scientist, this bothers me greatly. And so my work for the last some 40 years has been how to put this fundamental knowledge, how to put first principles-based physics and chemistry into the AI systems that we are building. It also bothers me as an engineer because mechanistic causal understanding is important in certain mission-critical applications such as diagnosis, control, and safety. And I cannot trust black box models there blindly because the cost of a mistake in our domain is high. For example, if Yelp makes a mistake in recommending you go to a restaurant, you didn't enjoy the food, you perhaps lost 2 hours and $200 maybe, but nobody died, hopefully. But when things go wrong in a chemical plant, it could kill people. Or in the failure of this control system in this Boeing, which killed hundreds of people, as we all recall. So in areas like chemical engineering, nuclear engineering, and aerospace, the cost of a mistake is potentially very high. And so we cannot blindly trust black box AI models. And so I divide the opportunities into 3 broad classes. One is these easy problems are those where you have lots of data, good quality data, and then you can use these easy to use machine learning tools that are out there, random forest or Bayes opt or one of those things. And they're not particularly difficult problems to do because people showed how to solve these problems 20 years ago. And it's already happening. People in the industry are already implementing these kinds of things in a variety of applications. So these are not particularly that hard. See, the hard problems are building these hybrid AI models. How do you combine first principles with data-driven techniques? Even though these things were also shown some 20, 25 years ago, we still have a long ways to go. And also building causal models, as I showed in our DKIT work, and in the PHA suite work and so on. So I think this combining symbolic AI with numeric AI is where all the big opportunities are going forward in chemical engineering and in fact in other engineering applications. And I think it'll take another 10 years or so to do these things easily, systematically, and routinely. And so this is where people are overestimating what machine learning can do and underestimating the challenges here. Harder still are those Watson-like systems that we built for pharmaceutical engineering applications, which I did not talk about, and catalyst design applications, which I did talk about. This is where you have to build domain-specific ontologies, languages, and compilers and whatnot. And again, these are hard problems, much harder problems, and this will take another 15 years or so. Again, people are underestimating the difficulties here and overestimating what ML can do here. So to summarize, in my view, there's been three major revolutions in modeling knowledge in chemical engineering. For a long time, chemi was a heuristic discipline, and that changed in the mid-50s with the arrival of Neil Amundsen, who's an applied mathematician turned chemical engineer who worked at the University of Minnesota. Amundsen and his disciples showed how to take ideas from linear algebra and differential equations and then use them to model process units, such as distillation columns and reactors, from first principles. So this is the first knowledge modeling paradigm, revolution, and that happened in chemical engineering. The second one happened with the arrival of Roger Sargent at Imperial and his disciples, who brought in ideas from operations research, particularly mathematical programming and optimization, MILP, MINLP ideas, to formally model process engineers now. In the first wave, you modeled process units. Now you're modeling process engineers, particularly their decision-making capabilities and modeling constraints. In a similar sense, it is my view that the third paradigm is the use of artificial intelligence. So the first one brought in ideas from applied mathematics, the second one from operations research, and now the third one from artificial intelligence. And this did not start 5 years ago or 10 years ago. It really started some 35 years ago with the work of Westerberg and Stephanopoulos and others from that era. And the new idea here was modeling symbolic knowledge and modeling symbolic structures and relationships in decision-making and also in modeling units and whatnot. So that is how I see AI fitting in chemical engineering. And as I mentioned, the challenges are in building hybrid models and causal models and domain-specific ontologies and languages and whatnot. In general, how do you combine symbolic AI with numeric AI is where the major challenge is, in my opinion, going forward. And I think this will take another 10 to 15 years or so. So let me stop at this point and acknowledge dozens of collaborators in the form of former students, postdocs, as well as colleagues, and a number of different funding agencies, both industrial and governmental. And I've shown figures which are taken from various Wikipedia sources, as acknowledged here. And I'm going to stop here and take any questions you might have. Thank you again for the opportunity to present our work. Appreciate it very much. Thank you.
Thank you, Venkat, for an excellent presentation. We are open to questions now. And what I would ask you is, if you have any question, you can show with your hand, the hand option, and then we will unmute you to ask the question, or you can ask the question through chat, and I will read it out. So I can see already that there is one question from, I will read out the question and then we will take the other questions. So this question is from Asad Shahir. He asks, or he says, thank you, Professor Venkat, for a very nice presentation. May you share some thoughts on some changes which undergraduate chemical engineering education in computing may undergo to utilize the recent developments in AI and machine learning? To you, Venkat.
Yes, thank you, Rafiq. Thanks very much again for the opportunity to present our work. And thank you all the participants for patiently listening. That's a very good question. In fact, that's a question that all chemical engineering departments all over the world are grappling with right now, because it's very clear that AI and machine learning techniques are here to stay and help. And we really need to get chemical engineers trained and educated on them. And for nearly, since 1986, I've taught such a course, AI for chemical engineers, initially developed at Columbia, as I mentioned in the talk, and then taught for some 20 years at Purdue, and now I'm back teaching it at Columbia. It's aimed at senior level undergrads and first year sorry, I think it seemed to have gone into mute. Can you hear me?
You're okay now again. We can hear you now.
Can you hear me okay?
Yeah.
Yeah, okay. So the answer is we have to find a way to teach these things. The curriculum is already crowded, and that means something has to be left out if you have to put in a new course. And that's the struggle that everybody is facing, but people are realizing somehow they have to make this work. So I do imagine in the next 5 years, an undergraduate course with sort of the title like machine learning for chemical engineers might be introduced. Some departments are trying those things out already in the US. And like I said, my course is along those lines. And in fact, I just completed a paper on it, what the syllabus should look like and whatnot. So I'll be happy to share that paper through Rafiq with all of you so that you can get an insight into what the syllabus should look like.
Very good, thank you. There was a hand from Moinuddin. Is he still there? Can you unmute him, please? Okay, you can ask your question.
Hello, Professor Venkat. Thank you for the presentation. I just got a quick question. Like, if somebody already has an undergrad in chemical engineering, like, if he wants to get into this AI and chemical engineering, like, what should he pursue? Like, masters or some of the courses or some crash course? I mean, what do you suggest about that?
Right. Well, many departments are now offering. Clearly you can go to computer science and do a master's in data science. Columbia University, for example, has a course like that, and many universities do. Georgia Tech has a very successful program. So there are a number of universities. Some chemi programs are beginning to offer a chemical engineering master's with a data science track. In fact, again, our department at Columbia does that. And so you could look at such chemi programs. The third option is there are excellent courses. If you are very disciplined and motivated, you can learn many of this material on your own through open courseware kind of resources such as Coursera and, or the MIT courses, where, I would recommend you need to do perhaps 4 courses. One would be a course on AI, then another course on machine learning alone, a third course on statistics, and a 4th course on natural language processing. And I would say a 5th course on databases. So if you do these on your own, you will have a pretty good start in machine learning. And then the rest you kind of learn by executing various projects.
Thank you. Thank you.
Okay, there are quite a few questions on the chat box, so I will read as they come. So the first one is from Parag, who says, I wanted to ask about the future of MILP. On one hand, they give global optimals. which is essential, but they are NP hard. What you think the future of this?
It's a good question. It's not going to go away. All the optimization techniques, whether it is MILP or MINLP, they're all here to stay. And, there are different classes of problems. For certain class of problems, those are the appropriate techniques. And there are some other classes where, the models are black box or derivative information is missing or is not available. Then you might use AI, machine learning techniques. So they address different kind of challenges. The other thing is there are some cases where these two can be combined also. For example, I believe in 2004, we published a paper with my student, Santochi Katare, where we did a parameter estimation problem for a complex kinetic model development, where the parameter estimation was actually done by using a machine learning technique, generic algorithms, combined with MILP. So GA actually did the global search initially, and once we identified regions of promising solutions, then the MILP went to work. So you might even find cases where these things are combined. So I don't think MILP and other things like that are not going to go away anytime soon, and they are going to be maybe even combined with machine learning.
Okay, so we have quite a few questions. I hope you don't mind answering them. The next one is from Shomesh. He says, thank you very much for the nice presentation and insights. The causal model you presented can really help out in mitigate industrial hazards, or are any applications from the process safety perspectives? Thank you.
Yeah, good point, Somesh. Yes, indeed. I didn't get into that. I think, mentioned briefly in one slide the use of causal models for process safety. I've had somewhere from 5 to 10 different PhD students who wrote their thesis on those kind of problems for process hazards analysis, for continuous processes, batch processes, synthesis of operating procedures, fault diagnosis, and alarm management and that sort of thing. So a whole bunch of papers published, and some of them I cited in my perspective paper, which I mentioned at the opening of this lecture, paper that appeared in ASCHE Journal in 2019. It's open access. I deliberately published it as open access so that anybody and everybody can have free access to it. So there are a number of references to work in the process safety area, and that might be a good place to start if you're interested further.
Okay, now I will go back to the hand. There is a hand from Kim Nielsen. Can you allow him to, please, Kim Nielsen, ask your question? Can you, yeah.
Yes, thanks a lot for a really good presentation. I have a background in inferential modeling for petrochemical industries. I'd just like your perspective on these newer methods to develop robust inferential estimators as opposed to using simple linear regression. How widespread is the use of these newer methods?
Good question, Steve. It is just beginning to happen because while neural networks and other such black box models are helpful, their reliability, extensibility, stability, and robustness are all into question. And so people are looking into those kinds of things. And that's where, for example, physics-informed neural networks come into play. So people are trying to build in as much first principles into them as possible so that the inferential modeling can become more reliable and become more stable and so on. we still, and these are the kind of things which will, like I said, will take another 10 years to sort out. Like I said, there are papers beginning to appear, but it's all case by case basis. And we don't have a general framework or a general theory of these things yet. And I expect that to happen in the next 10 years.
Okay, there's still a few questions left. I hope we can take all of them.
Sure.
So the next question is from Elias Martinez. He thanks you for a nice presentation. And then he asks, how do you actually incorporate first principles into AI models to build hybrid models? Could you elaborate more on this or provide a good reference?
Yeah. And, again, a very important question, very timely question. Lots of people are wondering about it. And, that in itself will take a 1-hour lecture, how to build first principles into AI models. So I can only briefly answer it here. Like I said, this will take another 10 years to really sort it out. We don't have a good theory or framework of this yet. But just this week at the Escape conference in Toulouse, France, my student and I, and also with colleagues from Aspen Tech, we just presented a paper on building hybrid models. So you might want to take a look at that. It just appeared. In fact, the paper was presented, today is Friday, right? It was presented on Wednesday. And so that's one place. Another one is a group from IIT Madras, under the leadership of Professor Raghu Rangaswamy, has published an interesting paper on building hybrid models. That also appeared in the last couple of months in the special issue of the AICHE journal on AI for chemical engineering applications. So that would, again, be a good place to start.
Okay, so I will take the next question from chat. And then after that, Brahim has raised his hand, so we will go to him. So in the chat, Abhishek is asking, first he's thanking you for a wonderful presentation. And then he's asking, let me see. When we talk about AI, open data sets in chemical engineering domain are very much limited in open internet, as most of them are either classified or confidential to companies or research groups. So even if we build AI models, will it be of any use with much of the data available?
Yes, very important concern, Abhishek. I'm glad you raised that. That is slowly beginning to change. In the catalysis area, for example, people are creating open data sets. And in material science area, also that is beginning to happen. So the community has recognized this need. And then these kind of open data sources are beginning to emerge. Of course, there is the US Patent Office database, which has a million reactions or so. So there are some things right there, right now in some areas, but it is a concern. It needs to happen in all areas, but that realization has set in and people are beginning to do that. So hopefully we'll be in a better shape 5 years from now.
Okay, so can you unmute Brahim so he can ask his question? He also has the question, I guess, in chat, but please ask your question.
Thank you very much, Rafiq. And thank you very much, Venkat, for this great talk. You have highlighted some of the risks associated with standalone AI systems. Do you agree that the future belongs to probably synergies between non-AI, robust PSE tools and AI? And if so, do you have any example in mind that you'd probably be able to share with us?
Yeah, again, an excellent observation. That's where when I mean hybrid AI, I generally mean all these variety of techniques, including first principles based models. So these are all application specific. You might do it one way for design, for example, and that too, one way for process design problems, another way for product design, materials design, and one might do something else for control, and yet another way for process safety analysis. So, and these are all the open questions there. What are the templates? What are the frameworks that one needs to develop so that such applications can be fielded more quickly? So these are the kind of things we should be working on, and these are hard problems. The easy problems, like I mentioned in my talk, is the ones where there are lots of data available and you simply use some machine learning technique. But not all problems are like that. And so much more work is needed to address these kind of challenges.
Okay, we have 5 more questions. These would be the last 5 we will take. Okay. The next question in chat is from Brian. I will not try to say the last the surname, but he thanks you also for a great presentation. And his question is, with respect to process control, there is recent literature with theoretical guarantees for safety, either through feedback control policies or with well-defined tolerances, either using reinforced learning or some hybrid systems. Given that these safety guarantees are well-defined, is it not feasible to use these models despite the lack of explainability in industrial settings?
Yeah, well, it's really application specific. If all those guarantees do exist, certainly those models become more acceptable than black boxes without such guarantees. And operators still would like to get some explanation or some idea about why a particular recommendation was made. It always makes them nervous when the system says something which they don't understand. And so this transparency and explainability is going to be there as a challenge. And then, despite all the guarantees and whatnot, if it's not too clear, that's always going to make people nervous. And also, it also depends on the cost of a mistake. If the cost of a mistake is not high, then people can live with that. They can live with black box systems. But if the cost of a mistake is potentially high, then they get more nervous.
Okay, next is a short question from Abhishek. Is there any way where we can link commercial process simulators like Aspen with an AI-based model so as to devise a hybrid model?
Yeah, actually Aspen itself is doing it. And Aspen itself is developing such toolboxes. You'll hear from them in the coming years. And again, I know the university groups are also playing around with such ideas. So that's beginning to happen. Okay.
I think this is probably the last question, unless some new question has come. So the last question is from Rishabh Jain. Your developed tech based on operating procedure synthesis, OPS, ITOPS. Does this tech, is it implemented, I guess, practically in any industry? If yes, which industry?
Right, yeah. It was actually implemented and delivered to the Searle pharmaceutical company based in Chicago in 1998. And some 25 process engineers were trained on it, and it was tested on some 50 different pharmaceutical applications that Searle was working on, and it was found to be very helpful. And so it was put to use. So, in 98 onwards, engineers were using it routinely. on their daily needs of synthesizing procedures for different processes. I don't know what the current status is because Searle got acquired by Pfizer and so on. And I also moved on from that area. Since we had done it and delivered it, I kind of lost interest in that area. So, and when we have a series of papers published in the late 90s on this, which describes the details, which you might find helpful.
Okay, so all the other comments on chat are basically thanking you for excellent presentation and answers to their questions. Maybe as the host, I can ask the last question.
Please.
And it may be just a topic for discussion. Do you think with AI, we can create a machine that can think?
Well, I have to return that with a question. Define thinking.
Thinking like a human.
Yeah. You know, I mean, that is the, you know, that's the $1 billion question, isn't it? You know, it's the question is more philosophical than it may sound. Humans also, we exhibit a variety of thinking modes. You know, some are simple gut reactions, and then some are analytical thinking, which requires long periods of gestation and whatnot. So, and this is related to the topic in AI known as artificial general intelligence, or AGI, and that is it used to be also called common sense reasoning, or use of common sense. Current AI systems don't have that capabilities. But that will definitely change in the next 20 years as computers get more powerful and as we get more data to train these things. But like I pointed out in my talk, just because a robot can do certain things, that doesn't mean it necessarily understands the knowledge deeply. Like I pointed out in the cheetah chasing a gazelle example, they exhibit those tasks very well, but they don't understand the deep physics and math that is behind it. So that is still a challenge. We are good at doing that. And so it raises a whole bunch of questions like, how is the neural network inside our head, what we call as a brain, which is the hardware, and the software is mind. How are they different from the silicon-based hardware and software? So, so these are all questions which need to be sorted out. And again, these are very hard questions. It'll take another 20, 30 years to make progress. So, it's a long-winded answer to your question, Rafiq, but then it's a difficult question. My own feeling is, computers will demonstrate an amazing amount of thinking that we see in humans, but in the coming years, and they will surprise us. So they will reach a point where it'll be hard to see the difference. And in fact, that's already happened in game playing programs and other such domains. But for all kinds of domains, that is still, that remains to be seen.
Yes, I asked this question also because I like science fiction, and many of the science fiction books, the villain is the computer that can think. So,
I know. Something like Terminator. Yeah. So,
yeah, or others. I mean, it's always the villain taking over, trying to take over. Thinking that the human is too stupid to continue with. But anyway,
it's not going to happen in the next 10 years, but it may happen in the 50 years.
Thank you. So, okay, thank you very much for this excellent presentation, and also for answering so many questions. I can see that Brahim still has a hand. Do you want to ask anything before I close?
No, I was just applauding. So I was just thanking Venkat and yourself. Thank you.
Okay.
Thank you. Thank you.
So I would like to first also remind all of you, if you have registered for the next webinar on 28th of June, that's going to be also a very exciting presentation talking about circular economy and sustainability, which are also very, very important for us. So please do not miss that webinar. Join on time. If you have registered, please do join. And again, once again, I would like to thank Venkat for this excellent presentation and doing the question answer despite your eye surgery. For all the participants, thank you for joining. For the Thai team who has hosted the webinar, thank you for your good work.